All right, so hello everyone. Welcome to the Machine Learning Center seminar today. Today we're fortunate to have Dr. Qi Wei from JP Morgan AI to present interesting research regarding point process related to financial applications. A quick introduction to Dr. Qi Wei is that he received his PhD in machine learning and image processing from the National Polytechnic Institute of Toulouse, University of Toulouse, France in September 2015, and the bachelor degree in electrical engineering from Beihang University in China. Dr. Wei's doctoral thesis is Bayesian fusion of multi-band images, a powerful tool for super resolution, was rated as one of the best theses at the University of Toulouse, 2015. Dr. Wei has worked on multi-band image processing as a research associate with Signal Processing Laboratory, University of Cambridge in the UK, and as a research associate at Duke University. He has also worked at Siemens Corporate Technology as a research scientist. Since 2018, Dr. Wei served as a vice president and machine learning scientist at JP Morgan. His research has been focused on machine learning, deep learning, time series analysis, computer vision, image processing, Bayesian statistical inference, and so on. Without much further ado, let's welcome Dr. Qi Wei to give the talk today. Thank you very much.
Thank you very much, Yo, for the introduction. Hello, everyone. We're very welcome to join this seminar. Today I will talk a little bit about what is done here to apply deep learning or machine learning to time series application. So specifically, as you can see here, we talk about the generative models based on point processes for financial time series simulation. So more specifically today, the use case will be like the limit order book modeling. I will spend some to explain what does that mean if you are not familiar with limit order book. So basically, there are three parts, but I prepare a lot of things. We will see how much time we have, and also at the end of the talk, I will show you some more cool demos. So the first part is about background about the financial application, about what is a limit order book and why we want to model a limit order book. And the second part is more about the preliminary about the point process, the counting process. Hawkes process. If you guys are already familiar with this, we can skip many parts here. And the third part is about the model theory, how we adapt this state-dependent Hawkes process and its constrained version to limit order book modeling. And also, if we have time, we can talk a little bit about the simulation and the parameter estimation. And this is part one. It's everything is about theory. So second, I also have a separate slides that is more about project results. I think in the very last 10 minutes we can go to some demo there. Okay, so what is a limit order book? So in the financial market, or especially in an order-driven market, so buyers and sellers they meet via a limited order book. So that is to say, the limited order book orders is stored in an order book. Okay, and it can be analyzed for algo trading, high frequency trading. So the applications are quite wide. It's like market making strategies, optimal execution strategies, and also like some statistical arbitrage strategies by the hedge fund. So what is a limited order book? Here's a quite straightforward realization what the order book looks like. So you have like the basically we have like the buy and the sell. So buy is a bid side, the ask side is a sell. Okay. And each color bar represents different prices. So if you walk towards this direction, on the right direction, the price is going up. If you walk towards the left side, the price is going down. Okay, and so we have for each price level, the height of the color bar represents the quantity of the order you are placing. So so naturally we will have the so-called best ask price and the best bid price. And the difference between this best ask and the best bid, we call the spread, right? So, naturally, when you try to buy a stock from the market, the price you see is something like this, middle price. We call the average between the ask price and the bid price. And in a very high level, you can read limit order book in this way. So this part represents like the the supply, and this part represents the demand. So this is more like the supply and demand balance. So I mean, like in economic theory, this is like the invisible hands which drive the price dynamics. So that's in fact the reason, the most why we want limited order book is so important for stock market or for equity market. So because the price dynamics is controlled by the interplay between the incoming order flow and the order book. Okay, so here's a basically a demonstration of how the order flow affects the shape of the order book. So the step one, here's this initial state of the limited order book. We have the buying order here and the selling order here. So naturally, usually the selling order, the price is higher than the bidding orders. And then you have, let's say, some buying orders coming and some and then we decide to deplete some most recent, most aggressive selling orders, and you can see this part is taken. So this part is kind of filled or depleted by the orders from the other side. We said it's a liquidity is taken, and then the spread is wide. The spread is become much wider than before. I want to kind of give you some numbers. So at the very stage one, the mid price is around 100. And after this liquidity is taken, you can see the spread is much wider and the mid price going up a little bit, right? And from time to time, we also have new orders arriving. So when you, for example, when you place a new limit order, it will put somewhere in the limit order book. And then inside the liquidity is the returns, and you have more orders return, and you can see the spread is becoming narrower and narrower. The final state will become like this. So this here the spread is even narrower than the beginning. So, but in practice, when you really buy a stock in the market, what you can see is only this price, it's mid price, and you can see from step 1 to step 6, the price in fact does not change that much. It's like just to have a I think it's just an increase from 100 to 100.5, just to have $0.5 change. But in fact, a lot of things are already happened by this liquidity taken, liquidity returns. The market is quite dynamics. Oh, okay, maybe a very high level. So in the financial, you have like the stock market, you have the FX foreign exchange market, you have the credit bonds market. But during all the markets, the stock market is the most active one, because people love buying stocks, people love trading stocks. That's why you can see the limited order book always have a very high volatility and liquidity all the time. Okay, and so as I mentioned, I mean, why this is important, because the price dynamics is driven by this order flow, and the price dynamics is in fact one of the most important factor for all the decision making for the traders. So what are we and how can we build a good simulator for the limited order book? It's not surprising that the existing solution is we use all the historical data. And this, in fact, is quite popular in almost all the investment bank market makers. And yeah, the historical data as a data simulator for reinforcement learning, backtesting, etc. But the problem is very, very straightforward, right? The historical data is just one single Monte Carlo run. So, I mean, if it happens, it happens. We don't have a time machine to go back to yesterday to run the market again. So that's, I think, one of the main problem. The second part is if we want to do like some quantum factory inference. Okay, this is in fact quite important for the pricing strategy. So especially for the large orders, this might not be a problem for us. I mean, for individual investors, if you want to buy Google stocks, 1,000 Google or 100 Google stocks, I mean, your action will not affect the price, the market that much. But as like JP Morgan or the other like Goldman, Morgan Stanley, these important market makers or executors in the market, all your action will affect the price very much, and you have to be careful about that. So that's why this is a huge problem for market makers, right? And let me summarize a little bit. So in fact, the market is a stochastic process. It is not a deterministic one. Instead of single Monte Carlo, and that's something it's not possible to be realized in historical data. And we are part of the market instead of merely being an observer. So our action will affect the market a lot. So what we really want to do here is we want to model the influence between arriving orders. So this is not hard to understand. So the financial market is quite different. If you regard these order flows, it's quite different than you waiting for a bus or waiting for a subway. Because basically the arrival of a bus or a subway will not affect the following one. But in the market, you can see that when people buy stocks, let's say you are buying Amazon stock or Tesla stock, and the price is going up, and more people want to follow, you have this herd behavior very obviously. And when the price is going down and the people are selling and more people are following and they want to sell, and you might have a market crash, the panic is spreading quite fast. So this basically tells that each event or each order arriving is affected by most recent history, or what happening now is affecting the future, quite interactive or active way, right? So we really want to model this influence between the arriving orders. So that means that we cannot use some homogeneous Poisson process. We need to use a non-homogeneous Poisson process, which means the intensity is excited, it's changed, or it's triggered by the events, the arriving orders. And we want to explore the market dynamics driven by the order flows. So when I mention the market dynamics, you can think about anything related to the market, not to the orders, like the current spread, or some order imbalance flow, order flow imbalance, something like that. And we also want, if we really want to make the model works in the financial world, we need to have a grounded mathematics sound and also explainable, easy to interpret model. Okay, so this is a little bit different from the black box. Let's say you use a neural network or deep learning strategy. It might give very good performance, but once you have a problem, you don't know which part you should fix. So interpretability is in fact something quite important to make it applicable to the financial use cases. So yeah, the proposed approach is a constraint state-dependent Hawkes process. We will arrive there step by step with some details. So okay, so far any question or comments? Yao, you collected from the audience, or?
So far it's good. Thank you.
Oh, it's good. Okay, so
yeah.
Let's yeah, this part is a little bit basic. I don't know how necessary I need to go through this, but maybe let's go to the point process definition, and I just emphasize a little bit of points here. So point process is basically a counting process, right? So we are counting the number of the arrivals, and if we for different event types. So here this DE is a dimension of the event space. So and for each arrival, we need to tell which event type it belongs to, and this is a basically accumulation of a number of arrivals for each event. And a Poisson point process, I think this is one of the most popular point process. I think still quite widely applied in the financial world. So a Poisson process, a homogeneous Poisson process, basically is with a rate lambda e is a constant, and it has the following three main properties. So the first is the initial counting number is 0, and it has independent increments. This is quite important. It means that the number of arrival within time t, and the t1, the t1 plus epsilon is same, and the distribution the same as t2 and t2 plus epsilon, right? And the number of events or points in any interval of length t is a Poisson random variable with a parameter lambda et. So this in fact give us quite this is a quite nice property, and that's why the name is a Poisson distribution, because the number of arrivals within a certain time interval is following a Poisson distribution. And natural derivation from this assumption from this property is that the intervals between arrivals will follow exponential distribution with parameter lambda e, and also some other interesting properties like the arrival times itself will follow Erlang distribution or gamma distribution. Right? So yeah, that's the basic Poisson distribution. And here's an example of what a Poisson distribution looks like. Yeah, I make this a very simple example just to let you have a very high level idea of how we are using it. So A here means ask, B is a bid. Okay, if you still remember, if you cannot remember, if you cannot tell difference between ask and bid, you don't really need to remember this. So one means buy, the other one means sell. So, but I will continue to use ask and bid because this is like the words we are always using daily words we are using. So the event space is quite simple. We only have two event type, ask and bid. The Poisson counting process, we have two event types. N1 means ask and N2 means bid. And the intensity lambda 1 is equal to 0.5, lambda 2 is equal to 1. So I put it here very clear, just want to remind you that this is not time, this is time invariant, okay? It's always a constant. And yeah, this is the intensity plot, and the arrivals you can see, well, statistically you have many more green dots than red dots. In theory, it should be like double times because the intensity is double times. Because the intensity of the lambda 1 is double times lambda 2. Okay, so we still have time. Okay. The next part is Hawkes process. As I mentioned, we want really to capture the excitation between or influence between the arriving event. Yeah.
Okay. There's a quick question from the audience. Ask if we could not have been part of the process and just observer, can we still use point process or Hawkes processes?
Sorry, can you repeat the first part? I missed your first part. So what if
we it's asking if we would not have been part of the process or just observer? I guess you are talking about what the action, our action will have an impact on the process.
Yes.
So I guess this question is about what if we're not, but we're just observing the process.
Great question.
Yes.
Yeah. If you are not part of the market, so your action will not you will not influence the market. It is possible to use well, first you still cannot use Poisson process because the market is the orders are still influence each other. Your order might not affect the others, but the orders from institution from JP Morgan, from Goldman, they will affect each other. I mean, because all the orders are executed by these large institutions or exchange markets. And but something which is nice you can do is you can do back testing without considering the influence of your inserted orders. I don't know whether I answered this question. I mean, for the modeling part, you still need to turn to Hawkes process or any non-homogeneous Poisson process if you want. But for the back testing part, you can do that. But I will show you later. In fact, the demo will show you that when this size of the order change, you can see how the market is affected. If the order is just the size equal to 1 or 2, it doesn't affect too much. But when the number of the orders or the quantity of orders is increasing, you can see the price is driven by your order very, very obviously. Yeah. I don't know whether this is it is clear for.
Yeah, that makes sense to me. Thank you.
Thank you. Yeah. So here's a ordinary Hawkes process. So the main difference here, I mean, instead of the intensity is a constant, we have this part. This part basically is we call the excitation part to consider all the influence from event E prime over event E. Okay. So don't be. I guess some of you, if you are familiar with point process, this is not this form is quite familiar. But some of you guys, if you don't do point process, don't be scared. I mean, this part is basically just a summation of all the events happening in the history. Okay. So and this kernel is Ke prime E. Basically, the kernel controlling the influence of process E prime over E. And if the E prime is equal to E, we call it the self-excitation. And if it's E prime is not equal to E, it means it's a cross-excitation. Okay, so yeah, here I give you one example. I skip the example for Poisson process one, so I think it would make sense a little bit more sense to talk about the example here. So for example, we have a two-dimensional Hawkes process, still the ask and bid, and this is the arrival time for the event type 1. This is arrival time for event type 2. Okay, and when you compute how do you compute the intensity? It's very simple. The lambda E is like for the ask event, it's a new 1. This is a constant, and then you just need to consider all the cross self-excitation and the cross-excitation. Okay, and this integral basically it's over the counting process, so it's basically just the sum of all the past events. And so, for example, you can write the intensity at time t equal to 7. 9 or 9 plus epsilon and t equal to 11. So you basically just need to count how many events occurring before this timestamp. So when t equal to 7, we can see that t1, t2, t3, t4. These 4 events are what occurred before. And then you have the 4 kernels here, right? And this first part, because and the subscript, in fact, is decided by the event type, whether it's a cross-excitation or it's a self-excitation. And when the time is increases from 7 to 9 or 9 to 11, you just add what happens following, what happens during this interval. Okay, so this is just to demonstrate how we can compute the intensity of a Hawkes process manually. And yeah, the kernel, for the kernel part, I mean, the exponential form is one of the most popular one, but it's not necessary to be exponential. But it has, the main reason I put it here is it has a very nice properties and easy to compute when you do the estimation later. So it's usually it's characterized by 2 parameters. We call it impact coefficients, which is alpha. This also tells how your intensity will jump when the new event, new order arrives. And the decay coefficients, basically this tells the decay speed of the new event. And each kernel is characterized by these 2 parameters. And yeah, and the set of a kernel can be written as alpha and beta, characterized by alpha and beta. When alpha is a diagonal, it means that we only have a self-excitation. So in a very high level, with alpha, you can understand it as a little bit like the covariance matrix, but it's not necessary to be symmetric. So each element basically tells you how the element E prime affects event E. Okay, so according to the definition here. So yeah, here's a, don't worry if you did not follow all notations. I mean, just to understand the high level ideas and maybe focus more on the figures or the numbers I put it here. So this is an example of the Hawkes process. The arrivals, different colors marks different event types. And you can see that the main difference here is the intensity is not too constant anymore. Every time you have one event arrives, you have a jump of the intensity, right? For both events, because you have the cross and self excitation for both events. Okay, let me yes, and can we use this directly to the limit orders modeling? Oh, very unfortunately, it's not enough yet. So the pro, I mean, let's summarize a little bit the pros and cons and why we cannot use it. So the intensity are governed by the event occurs and point arrivals, right, and the self and mutual excitation. This part is very nicely captured in this model. But the some part we are not very happy is the Hawkes process. They are unable to incorporate any endogenous state variables described in the limit order book. What does that mean? I mean, imagine that when I show you this table, this figure, it means that when you have an event arriving, no matter what is the market looks like, or no matter it is for Google stock or Amazon stock or for JP Morgan stock, you have something similar. Basically, it does not depend on the current markets, or the current market state or the spread of the market. Like this stock is popular or not, is the liquidity of the stock or the order flow imbalance of the stock. So this is like something does not directly related to the order itself, but it's more like the environmental state. Okay, so this part is missing. And specifically, the arrival rate of the orders in this model is not influenced by the state of the limit order book. That's why we want to incorporate this state in the limit order book model. That's why it gives us this state-dependent model later. Okay, I don't know. Any questions so far? Yeah.
Yes. So here's well, actually, somebody asked a question and he said, "Never mind, that was cleared up." Yeah. So these events are on the events marker. So these are mark the process, right? So mark the point process.
I understand that. Okay. If you are familiar with mark point process, it's much easier to understand. So this state, I'll explain that part later. Okay, when I really introduce state dependence one. Just to maybe a very high level, state dependent Hawkes process is one special case of this is so-called hybrid marked point process. Yeah. So a main difference between the state and the mark is mark you can regard it as an attribute of the event, right? You have one order, you can as ask and bid, or the quantity. This can all be modeled as a mark. But the state here is not necessarily directly associated with the event itself. It can be something else. For example, it can be the let's see, the Nasdaq index today. Okay, it's not necessarily. It can be like the GDP. I mean, this is or the temperature even. This is not necessarily associated with your arriving order or occurring event. So this is one of the main difference. So usually, if you have to think about it carefully, you can think that the order arrives and with many marks, and this state change or state jump happens just after that. It's not exactly simultaneously. I will explain you later. This will be very clear when you go to the definition of the state-dependent Hawkes forecast here.
Okay, great.
Yeah. So yeah. So the pair, this n and x, n is a state. N is an event. Is a point process with events, calculated event type, and x is a state here. So this pair is basically a state-dependent Hawkes process with transition distribution phi. Okay. So what is this? Let me first explain these two parts. It might be easier. So the base rate vector, if you remember, this is like the baseline, the background intensity part of the point process. And excitation kernel, I have explained you guys, right? This characterizes the influence of each other. And the x is a state, and it follows a Markov transition matrix. Okay, it basically is a Markov chain. And this transition distribution phi basically characterizes how the state will jump. Yeah, this basically, so the point process part has this intensity lambda. This is no big difference with what I showed you before, but there's one minor change here. Is maybe you have noticed that this kernel, it depends on the current state. Okay, oh sorry. This kernel depends on the current state. What does that mean? So this means, for example, when the spread is equal to 1 tick, the influence of the event E prime over E is different from when the spread is larger than 1 tick. So this, in fact, makes much sense in the financial market. Because it's like when this stock is popular, people want to buy, and in fact, your action, the influence of your buying action does not cause that much influence on other. But everybody knows it's popular. But when this stock is like not that popular, and you place a big order there, then the market will have a much will be much heavily influenced by your action, because your action is kind of normal lay words, like your action is a little bit weird. It's right, because this is not a very popular. So the current state basically affects this excitation, self or cross excitation very much here. But in fact, this is it's a little bit complex, but if we really give an example, you can see it's quite straightforward. Yeah, X is a piecewise.
Dr. Wei, quick question on the previous slide. So the first is, can we treat this as a conditioning on the hidden states? So because the kernel depends on XS is
great question. It is you're right. This can be characterized by conditional function, but it's not hidden. It's observable. So this X is it's a conditional distribution. You can this is basically already a conditional distribution, but you are right. This kernel depends on the current state.
Mm-hmm.
I think the example here will be very clear. So I jump a little bit. So when I decompose this term from here to here, you can see I put the state in the superscript. So 1 means that the current state is 1, the 2 means the current state is 2. Okay, so this basically tells that the self-excitation at state 2 for state 1, and this is self-excitation for state 2. Mm-hmm. So the main difference between this model and the previous Hawkes model is that for each excitation term, you need to multiply by basically the dimension of the state space. Before, you remember, we only have like two terms. Now we have like 4 terms here.
I see.
This is exactly what you said. It depends on what your current state is.
Mm-hmm.
Okay. Yeah.
Okay. Another question is how to evaluate the V background V1 here. So the baseline intensity, I assume.
Oh, this one? Okay. Yeah, good question. I think this part is in the is an estimation part. I can tell you all the parameter. The answer is all the parameters are learned from the data. So all the parameters, the new E is parameters we are learning, and the alpha and the beta, if you remember, characterize these kernels are learning, and this transition distribution also joint learning. So the parameters to estimate, including the baseline intensity, alpha and beta, characterize the kernels and the phi matrix. So this is the four parameters or four group of parameters we need to estimate from the data. Yeah. And don't be scared about this. I mean, the estimation in fact can be done quite an easier way or straightforward way. I can go through that part. It's interesting. I mean, the feedback is a little bit different. When I give the talk within the firm, nobody really cares about estimation. They ask more about the business sense of. But you guys, I think, more familiar with the model and the algorithm. Yeah.
Yeah.
I'm very happy you asked the question.
Yeah, great. So looking forward to the estimation. So quick question, the estimation is done by maximum likelihood or least square or some other metric?
Sorry, which one?
The estimation of the parameters are still done by maximum likelihood. You try to write the fit function.
Yeah.
I see.
Yeah, MLE. Yeah, yes, yeah.
Okay, sounds good. Thank you.
Yeah. So I think this part is a little bit more business. So instead, this is a point process. This is a state-dependent point Hawkes process we want to use to model the order flow. But remember that we don't really have like in practice we also have this kind of daily intraday or daily distribution. What does that mean? This is like I plot the number of orders per day for almost 1 month, and you can see for some day you have many more orders than the other days. This is no surprise if it's like before holidays or it's Friday. I think here you have maybe the Memorial Days or Labor Days. The market is much less active than the working days. And also this we have this intraday distribution. So this is like when you open the market is open and the market is closed. And usually when the market is open and the market is closed, you have some peak. So you already have this the convex form of the order of the how can I say that? They have a special name for I don't remember. Okay, so I mean this intraday pattern is also quite popular, quite obvious in the trading market. So that's why besides this state-dependent Hawkes, we also have this intraday and daily. That's why I call it a modulated state-dependent Hawkes process. You can think this is more like the high frequency part. This is like the high frequency. This is a medium frequency. This is a low frequency. Okay, so this is a long term. This is a mid term. This is a short term. And GT usually we use a piecewise function to describing the intraday. I would prefer skip this part. This is not this is more for the applications, and the daily factor we can model it with LSTM. Any state space model is applicable here. Okay, so here's another example to show how the state dependence Hawkes is computable. I think we can skip this part. Something I want to mention that as you mentioned, the kernel depends on the current state, but it does not necessarily mean that we need to double the number or triple the number of the kernels. We just need to make a selection. Like for this event, we check the state. If the state is 2, we only keep this term. Okay, we only keep the term for state 2, and just cross out the one part. So I put this because it's easier to understand. I mean, first we expand it and then remove the part which is not does not qualify for. Okay, the same for this part. Here's the example. I think this is a quite interesting example to show you guys how the state-dependent Hawkes works. So imagine that here you have one asking order arrives, right? And you have a jump of the right and the green, so asking and the bid. have a jump at both. But notice that the jump of A is higher than the jump of B, right? Because this is the asking order. And the state is 1. The state is equal to 1. But when the state is equal to 2, let's see, select one more here. Let's this event. Okay, this is still an asking order, but the main difference is the current market state is not 1, it's 2. So the state is like the spread, it's more than 2 ticks. So here you can see you also have a jump for both asking and bidding intensity, but the jump of the bidding orders intensity is much higher than the asking orders, right? So here basically means that we have a much stronger cross-excitation than the self-excitation, basically characterized. So alpha 2 is basically the excitation kernel excitation coefficients when the state is equal to 2. So and 2, 10. So when at the state 2 you have a much stronger cross-excitation than the self-excitation. That's the part I want to emphasize a little bit. And we are very close, but still, this Oracle state-dependent Hawkes process is not the one we directly applied for the middle notebook. So why is that? Here is more related to the execution logic. The first part is the distribution of the events is not, in fact, not explicitly constrained by the current state. So what does that mean? So one example is the occurring event might violate the execution logic. That is, an aggressive order will never arrive when the spread is equal to 1 tick. Okay, I prefer to skip this part but the high-level idea here is when the market is in some state, basically means the probability of some event occurring is almost 0. An analogy to understand this, like you imagine that your inventory is you only have 100 Google stocks, and then people are placing order, let's say they want to buy 200 stocks. So it is not possible to have this kind of order flow conditional on you only have 100 stocks, right? So this kind of constraint is not considered in the state-dependent Hawkes process. And also the other one is the state transition. It is not a constant matrix and should be driven by the interaction between the order flows and limited order book states. So basically here, sorry, I didn't know, I skipped this part, but this is like, this tells you how the state jumps between the different events, between the different states under different events. Okay, to echo what your comment. Sorry.
Yeah, Dr. Wei, sorry for interrupting. So there are a couple of questions, I think, for clarification. One audience asked, how does kernel K depend on the state XX? Okay. So you had the specification before, I think.
Yeah. So the question is how K depends on the current state, right?
Yes.
Yeah. So let's say this K12 means this is a cross-excitation with the influence of event 1 over event 2, right? And if we don't have this state, it is same for all the cases. But when it's conditional on the state, you have to check the state at time s. So if the state, let's say the xs is equal to 1, and you need to use the kernel, condition on this. I mean, the kernel with a state equal to 1 and the kernel state equal to 2 is different. So you can think you have two groups of alpha and beta to estimate here. Is that clear? So here is an example. I mean, you have this alpha 1, alpha 2. Alpha 1 means characterizes excitation when state equal to 1. Alpha 2 characterizes excitation when state equal to 2. So you have two more parameters to estimate.
Yeah, absolutely.
Okay.
The question is, some people ask a clarifying question. So the purpose here is we're going to estimate the factors of the point process using maximum likelihood estimate, MLE, and once we have the point processes representing the underlying model, we can use it for prediction and analysis. Is that right?
Yeah, good question. I will not claim we are using it for prediction. I will say we are using it for simulation. The main difference is because basically we are trying to model the intensity, right? Prediction can be modeled as supervised learning problem. Here's more like a generative model. So, but we are trying to model the condition distribution, but still it's a distribution. Okay. I think after the demo, it's much clearer how this is being used. You can think that we are trying to predict what happens conditional on what you have up to now in a very short time. But if you really want to use this model to predict, let's say, what's the Google stock price will be in 5 minutes, it's not necessary to use this model. You can use some other models. I think that might be more efficient. You only build a model for price dynamics. That's enough.
Mm-hmm.
Yeah. So okay. I think we have time until 1:15, right?
Yes, we have time.
Yeah, I just want to make sure I show the interesting. Okay, I prefer to skip this part. It's a constraint. Well, this is highly related to the market execution logic. That's why we have this different event types, and we have this different why some parts are fixed to be 0 and 1, some parts are estimated, and also this is symmetric. Okay, let's skip this part. Yeah, some of you asked the also skip the simulation part. So let's go to the estimation part in case you guys are interested. So the target is we want to estimate the transition probability, phi and the base rates and the kernels jointly, right? The kernel including the alpha and beta I mentioned. Yeah, let's see. So the solution is quite comfortable. In fact, we can express the likelihood as a two separable form with respect to phi and nu and theta, and maximum the likelihood is conveniently can be achieved by solving two independent optimization problem. And so the one with respect to nu and theta, I mean the point process parameters, is no harder than that of ordinary Hawkes process optimization problems. So what does that I assume you're already familiar with the Poisson and multivariant Poisson and multivariant Hawkes. Let's jump here. So this is what the likelihood function looks like. So we take the log algorithm, and it can be basically decomposed as two parts. The first part only depends on the phi, which is the transition matrix of the Markov chain. The L2 is a log likelihood of a Hawkes process. This is an Oracle Hawkes process. Okay, so no difference between this and the Hawkes process I show you at the very beginning. And also the data in this part is only the event and state part, and in the L2 term you have the timestamps. That's the most important thing. So yeah, what I want to say here is that the model seems very complex and a little bit coupled with the state. The state and the event type are very tightly coupled. But when we really write the log likelihood function, we can find that it's no harder than the estimation of the Oracle Hawkes process. So and this part is if you are familiar with the Markov transition matrix, this can be computed explicitly. In fact, you have closed form solution for this, right? No.
A quick question, Dr. Wei here. So here you assume the temporal influence is exponential decaying. Is that?
Sorry.
The temporal kernel is exponential decayed in time. That
yeah. Well, for this likelihood, we don't have this assumption. It does not matter which form. You can also use power laws kernel if you want.
It's 13 hours.
Yeah, and yeah, because you see the lambda et, I did not give explicit form of this intensity function here. Yeah.
So I guess the integral, there's an integral over t.
Oh yeah.
So this usually causes computational challenges, but here this is fine because you have like a one-dimensional integral, so you can do this.
Yeah. Okay. Yes, you're definitely right. I mean, this part is most consuming. That's definitely correct. If that's why, yeah, I mean, currently we are using kernels, but we are using multiple kernels, not only one kernel. So multiple kernels for different, let's say, decay rates, to capture like the capture. How can I say that? It's like long-tailed effect in some cases. Yeah.
Got it. Yeah. Thank you.
Yeah. Okay, so yeah, the log function can be written like this way. Yeah, I think this is a proof sketch. We can skip this part. Yeah, and what is the estimation of the can be decomposed into two form. And to estimate the phi matrix, we have the closed form solution. And for the nu and theta, it's this is no difficult than the exactly the same as the MLS maximum maximum likelihood estimator of an ordinary Hawkes process. Okay, so okay, this is let me. We still have 10 minutes, just the right time to. Okay, so this is more about some interesting. Let me skip. We come here. Yeah. So this is a simulated data. I want to show you something. Some data are generated from this simulator. You remember that at the very beginning I showed you this daily effect of different accounts of for each day. And you can see that the generated data, in fact, matches the distribution of real data quite well. And this is this is some statistics, a spread. You can think about this as a multi-distribution of your generated data. We want to show that simulated data is close to the real data. This is a joint distribution of the event and the state or different event types. Yeah, under this is on the state 1, this is on the state 2. Yeah, and this is the most exciting part. Okay, so imagine that this is some historical data, right? And this is a stock price. It's going up here. Again, the blue curve here means asking order, and the brown curve means it is a bidding orders, the bidding price. So usually you have a gap between these two price, that is a spread. And for example, we want to see what happens if we insert order here. So you can see that you have a kind of an upwards momentum to push the price to go up, right? So and if we put an asking order, asking means a selling order. If we put a selling order, we hopefully the price should be either going the up forwards momentum will be smaller, and the price will be influenced by this order. And this order is large enough, we expect that the price will go down instead of going up, right? So this is something really simulated from order. So first we insert an order. The size is just 100, which means it's not a very big size. And each flash is one Monte Carlo run. It's one realization of the simulator until this order is filled by the market. And you can see usually this order cannot survive longer than, let's see, 50 seconds. In some realization, you have a probability to generate other paths. And let's increase the, again, this is a selling order. So this order is supposed to drive the price down, okay? And then let's increase this order size to 1,000. And you can see the surviving time of the order is a little bit longer, statistically longer, and you have a high probability that the price is driving down in some simulations. And let's make this order size 10,000. And you can see the survival time is much longer, and in most cases, the price is driving down downwards instead of going up. So with this kind of I would not say this is a prediction. It is more like a counterfactual inference. So the traders want to know what if I place a big order here? How the price will go down? And this is only the animation to still show like different realization of the past. And this is more statistically stable in that we increase the order size slowly, like from 1. So 0 means that basically you don't insert anything. 0 means like an original path, and we increase the size from 100, 1,000, 500, 5,000 until like 50,000. Okay, these are really large orders, and you can see that again the inserting direction is still the selling orders. That's why the price is going down, and after and then you can see. Okay, let me explain. So the vertical, the vertical is the price change, and the horizontal is a time. And each curve represents the different size of the orders. And this error bar is because we run like 100 simulations and make the average. That's why you have this error bar. And you can see, let's see, this is a 50,000, and you can see the price is driven much lower, right? And this 25,000, it's around here, and 20,000. You can see the smaller the orders, the less influence of the inserted order to the price dynamics. Okay, when the order size is small enough, I mean, basically you don't affect the price that much. Yeah, this is basically a price drift, the same thing. Yeah, this is as I mentioned, when I mentioned the time to fill the order means when you place a buying order or selling order in the market, and they have another order from the other direction, they might fill your order. So this is like the time to fill the order, okay? And you can see with the increase of the order size, the time needed required to fill the order is much longer. Okay, we have time. And yeah, this is a percentage of being filled. Okay, when you place a like limit order in the market, after like a certain time, if it's not filled, it will be, if you guys are using Robinhood or any trading software, you really ask you tune like end of the day or tune some specific date, and after that date it will be cancelled or it's a timeout. And you can see that this filling ratio, so when it's timeout, it means it's not filled. It's when the order size is small, it's have very high probability to be filled. But when the order size is really large, the filling ratio is much smaller. Okay. Yeah, that's pretty much what I want to discuss today. I'll make a very short summary, and we leave like 5 to 10 minutes for more questions. The sdHawkes process basically enable us to model this two-way interaction between the self-cross-excitation pointing process governing the temporal flow of the events, and a state process describing the system. The system is basically the market. Okay, and the limited order book generator, the state-dependent Hawkes simulator can generate a limited order book which encapsulates the feedback loop between the order flow, the orders, and the shape of the limited order book. Basically, this part is more like an interpretation what does in the financial background. And a maximum likelihood estimator of state-dependent Hawkes process can be easily extended from the MLE of the ordinary Hawkes process. Yeah, I mean, the simulation part we don't have time to discuss today, but if you guys are interested, we can talk more in the Q&A. And the real data, the state dependency indeed is significant. And some future work, in fact, we are doing is this is also no secret. I mean, so more granular event types and states, deeper level orders, state modeling, higher dimension. And in fact, I think y'all make a very good point. I mean, we are in fact trying to merge these states with marks. So there will be like the marked state dependent Hawkes process for the real model. Yeah, I mean phase 2 model. Yeah. Yeah, that's pretty much what I want to talk today. Any questions?
Great. Thank you so much, Dr. Wei, with a round of virtual applause. I wish you were here so we can feature a nice lunch or something. I guess there are some additional questions from the audience. His first question is, isn't restricting the kernels to fixed function restrictive? The current state and history can be modeled with any autoregressive model such as LSTM or transformers, allowing for better flexibility. This is the first question. What would you on that?
Yeah, I think that's a very good point. Yes, you can use if this is a little bit like the amortized inference, right? So you instead of estimating the parameters directly, you assume that the parameters is generated from your historical data. So you are saying that we don't estimate the alpha, beta, or phi directly. We assume that they are the function of the most recent history, and you can build either LSTM or CNN to model that nonlinear transformation. Yeah, that's also something in fact we are trying.
Oh, good.
Yeah.
All right. The next question is, since you mentioned that you are using these models for simulation, I'm curious on how accurate they are in long term, as the stochastic process being considered are doubly stochastic, means that it's stochastic in time and depend on previous event. This is
I'm
about
sorry, can you repeat the last part? I missed the last
So the
part.
question asked, do you think how accurate the simulation model will be in the long term, as the stochastic process is doubly stochastic, means that it's stochastic in time and previous events. I guess it depends on previous. Is this going to direct?
This is a great question. But what I want to clarify, when you mention that the model is accurate, I assume that you are talking about something supervised, because when it's said it's accurate, I assume you are comparing with some ground truth and a computer MSE or something. Here it's a little bit more, let's see, the setting is a still generative model. We want to propose a interpretable model to model the market, to characterize the market. And this is also a very good, similar question from our stakeholders, and they want to see how can I evaluate the model. And that's why I showed at the very beginning, we showed like some results, like the statistics of the generative data to compare with the generative data and the real data, and show that they are similar. But that's not enough. And what the traders or the quants really want to see is that when I take some actions, the response from this simulator should be no different or no much difference from the response from the real market. So this is really something hard to justify. I mean, only the traders use the simulator, and they can tell you, oh, this result makes sense. So that's why I show you guys the results when I insert this order. The price is driven down or the price is driven upwards. This is like some test from the traders, as per the traders' request or the requirements. We have done to demonstrate that it makes sense to use this simulator as a kind of like an environment for reinforcement learning. Yeah, and the JP Morgan are really building something like this, called a deep hygiene. And you have a arXiv paper, you have the paper already uploaded to the arXiv called deep hygiene. So, and they really require a possible environments to be offered to the agents to learn the actions to maximize the rewards. Yeah, I don't know whether this is this can answer your question, but this is more my points.
Yeah, that's helpful. Thank you. I also have my last questions regarding the first part. In the end, you have the MLE estimation part. Sorry, still asking about estimation. Is that this can be done standard method? You had one slide, I think you showed very briefly, which it's this. So this is done in closed form, or what is the?
Yeah, this part is done by closed form. And this part is you need to no. This is not a solution. Basically, this is I want to say that this is this is exactly like you solving a MLE for multivariate Hawkes process.
Mm-hmm. What is this EXX prime here?
Oh, sorry. Yeah. So X, it means state. State means X. Okay. Let me think a little bit.
So I see. This is like a transition probability.
Yes. You got it. Yeah.
But if I understand, sort of like it's like a hidden Markov model, but the transition is Markovian, and so this is like a transition probability of the states, and then you could estimate one Hawkes for each state or something like that.
Yes, exactly. Yeah.
Good. And then 11 is always Sorry, go ahead.
No, I'm okay.
So in equation 11, you have to solve the nu and the theta, I guess, to control the, okay, so you're saying this is the log quasi likelihood of n.
Yeah, exactly. That's a very accurate description of the log quantity quasi likelihood objective.
Is this 11 a convex optimization problem, or maybe not?
Great question. So what I'm sure is if we fix nu, okay, we don't estimate nu. This is a convex, and the lambda e is assumed to be exponential. That's a convex problem, and it's easy to prove. But if you have nu here, no, it's not necessarily be convex.
Nu controls the decay. which is the exponent of the exponential or something.
The nu is a baseline, and the theta is you have the alpha and the beta to into the kernels. I'm sorry, too many notations. It's easy to it's okay.
Yeah, that it looks pretty familiar. Good. All right. So sorry for asking a lot of questions, but I think this is really helpful. And some audience ask, is it possible to share the slides?
I'm sorry. I mean, the slides they have some constraint on this. I mean, but there's one paper, in fact, explain this model very well, because this here you have some about the business insights in what JP Morgan is doing. I have to go into another process to really to share the slides. I can try, but it's very hard to.
Yeah, I understand. Usually for the companies, this is the intellectual.
Yeah, I mean, one more thing I can do is I can remove many like the financial part, but yeah, this is something I might be able to do, but I still needed to kind of ask for them whether it's possible to share this.
No problem. That's completely understandable. Thank you so much. All right, so let's see if there's no further question. I think we are just in 1 hour. It's a good timing. Thanks a lot to Dr. Qi for a very, very interesting talk, very exciting topic and very illuminating explanation. Thank you very much. And thank all the participants, thank all the audience for the great questions. Thank you very much.